How's it going? To catch us up to speed, in the previous video, we loaded in a GLTF file, which was all written in JSON. That's JavaScript object notation. We parsed the contents of that file and showed how to read it, basically, and that's all fine. Now in this video, we're going to be dealing with binary files. So a GLTF file will basically give you the structure and the meaning and semantics of all the data, but you still need somewhere to keep your vertex data. So that's the purpose of a binary file. Now, if we were to try to open this, it's completely meaningless. It's unprintable. If you look in the linked code, we'll have a start point which looks a little bit like this. It's basically got nothing, but we have some goals. So I'm going to take that binary file, and just so this has some meaning, I'll compare. So right down here, we have a mesh with some attributes. These link to some accessors. So an accessor is some sort of procedure for retrieving information. An accessor is going to look at a buffer, and in order to do that, it's going to need a buffer view. So for instance, we look at position. Position is accessor index 0. We look at the first accessor. It's this one here. We have vec3 is the data type, and that is referencing buffer view index 0. So we look down at the buffer views, index 0. These are all, as you can see, referring to the same buffer, the same binary file. So we can see down here, we can grab all this information from the JSON file, no worries. But the stuff that I'm really interested in is this byte length and byte offset. So all of the positions, normals, texture coordinates, all of that is actually baked into this file at various offsets. So for that reason, I've picked out some goals. First of all, we definitely want to open a binary file and read all of it. Great. Then we want to, what is this? Offset of 288. So the offset of 288 is buffer view 1, which if I look back, buffer view 1, I think that's the normals. Yeah, it's the normal data. Okay, so I want to look at the normal data and I want to parse it as a bunch of vec3s, and then just for flexibility, I'm also going to parse it as a bunch of floats. It's the same stuff, no worries, just to verify. And then I'm going to look at the integers. Now the integers are these scalar things. There's 36 of them, and they are the indices. So that's sort of the roadmap. Let's take it nice and simple. What I want to do is I want to open up this input file stream, and I want to read its contents as a set of bytes. A character is a raw byte. All right, so first up, I will open up the file and get its size. Now I'm going to specify a few things. First up, I'm going to specify that I'm opening a binary file. And secondly, I'm going to specify that I want to open this up at the end of the file. The reason for that, this is a classic trick, is you load in, starting at the end of the file, you read the value of the playhead, so to speak, and that gives you the number of bytes in the file. So this 8 stands for at the end. And of course, because these are options, we can chain them together with bitwise OR. This tell G and seek G will set the position. I don't know what G stands for, but it will set the position of the playhead, if you think of this like a tape. So we get basically where we are, the time code, so to speak, and then we go back to the beginning. So we're ready to actually read the file. Now to actually read the file, I'll use the following command. So in order to do this, we need to put in basically a pointer which will be populated. Now to get a pointer to a vector, we'll use the data function. So we'll go, whoops, wrong one. yeah, the data operation. And then we need to know how many things to read. At this point, we can close the file. At this stage, I'm going to be sort of talking around this a little bit because it's a great topic for beginners, I think. So I'll just do some printing. Now I'm going to get a few parameters. So I'll get the number of vectors that I'm going to read, and then the offset into the byte array to read from. So the fundamental memory size, I guess, is the byte, and this has come, it's actually come after a previous 24 vec3s. So this is a fun little exercise. How much data does a vec3 take up? Well, I've just grabbed my calculator right now. I have, of course, 3 elements. Each element is 3 floats. So that's 12 bytes for a vec3. And then just to check, if I have 12 bytes per vec3 and I've got 24 of them that I'm going to read in, yeah, the math checks out. That is 288 bytes. Just a good thing to know. When I was learning this stuff for the first time, those little touch grass experiences really helped me wrap my head around it. So anyway. Now at this point, because I'm going to be dealing with vec3s, I should probably include the GLM stuff. You may notice I've actually gone ahead and put that in the dependencies folder. So no problem, we've got that right there. We're almost ready to go. Now, I just want to talk about something which is probably pretty important, and that is the difference between resize and reserve. So you'll see that I'm using resize for my vectors. I probably need vectors too. I should probably include that. Okay, great. So I'm using resize and not reserve, and I'll show you what happens if I use reserve. Well, looks like I have to clear these out. Okay, so I've got a standard vector, and currently there are 2 variables which are super important, size and capacity. Okay, now the difference is capacity is sort of how much memory is allocated should we need it, and then size is how much memory is actually being used. Now if we step over, we're going to reserve some amount, and we can see that now we can use up to 840 bytes. Okay, no problem. But look at this. So I go step through, and now I'm going to read all this data into my vector. When I do it right now, look at that. Nothing changed down here. Nothing changed. And the best way I could explain this is that the underlying data array, the underlying data pointer, is not big enough, is not affected by a reserve operation. So whereas if we were to continually keep pushing things onto this vector, it would size up no problem without reallocations, all good. In this case, we are not doing a vector push. We're actually sort of treating this as a raw pointer, which means if this thing doesn't have the size for it, it's simply going to fail. So as a counter thesis to that, as a counter example, now we see we have the same sort of vector structure, and then we resize. This fills it with a default value of all zeros, no problem. But then, watch this, when we go down and we read, now we have got some actual data in there. Isn't that cool? Okay, so that is why I'm using resize and not reserve. But that brings me on to my next point, because we are ready to read all of those floats. Sorry, vec3s. So what I'll do is I will use the mem copy operation, we need to specify a few things. The pointer destination, which will be filled up. What I want to fill up is my fetched data vector. And then we want the source pointer where this will be copied from. And this is going to be copied. Oh, this is a little tricky here. What I'm going to do is I'm going to get my byte data. Now remember, this gives us a raw pointer. But then I want a raw pointer which points to a certain offset within that. So if you're not familiar with this, what I can actually do is if you add a value to a pointer, that will point to some future point in the list. I mean, this is either like new information or it's talking around in circles. I'm not sure. Let me know. Was that explanation helpful? But anyway, so what this will do is it will go into all the basically the file that we loaded, add that given offset from it, and copy this many bytes into the vector. Provided that all worked, the vec3s should be in there, so let's go and print them out. A lot of fun there, but really all I'm doing is I'm putting these angle brackets and inserting the numbers just like we would to display a regular vector. So I'll give this a shot. There we go. And as you can see, we have got, yeah, I mean, these look like normal vectors to me. And note that we can sort of see the same normal vectors being repeated multiple times. This is because I believe the model, will be using indexed drawing. And so that's sort of unavoidable. Okay, so no problem. That is the vec3 case. Now let's do this instead as a bunch of floats. I mean, it's surprising actually how little of this changes, because with my byte data, that's a whole bunch of raw data just sitting in there in memory, in consecutive memory locations. Like you just start somewhere and keep going. And it doesn't matter whether you are copying it to a bunch of vec3s or a bunch of floats. You're copying from one contiguous location to another contiguous location. So very little actually changes. Now I'll just go ahead and print all of that out, and I'm going to use the same sort of operation, the same sort of formatting, which means I'll be stepping in 3 at a time. There we go. Provided I haven't made any major mistakes, this should pretty much give us the same stuff. Give that a run. Aha. Alrighty. So let us investigate. All right. Can you see the error? Just some silly thing. I should have resized to the float count. Alrighty. Excellent. Well, that seems to work. We got the vec data. We got the float data. It works the same. We loaded the same data from the same file. No worries. Okay, now let's get some integers. Just being mindful to set a different offset. Now I need to be very careful here. This is an easy mistake to make. When we think integers, we would typically think 32-bit integers, but if we check this description for the buffer view, here we are, we're taking up a byte length of 72. So if I have 36 integers and they're taking a byte length of 72, that would indicate that every integer is taking 2 bytes, which would make them 16-bit integers. And so what I'm going to do is I'm going to read them in as 16-bit integers, just like this. I mean, that's pretty much it. We're going to read in 36 integers at a different offset. We go ahead, memcopy them in, and print them out. And this is what it looks like. There we go. So it's probably a good exercise to go through this and check that there's nothing crazy. For instance, if these were signed integers, not unsigned, oh, that's pretty funky there. But that's because I'm going up in threes. It's not measuring the I properly for printing. Anyway, if these were signed and not unsigned, and then we had a negative number, when those bits are interpreted as unsigned, becomes really large. So if we had some crazy big numbers here, that would be a problem. But I went through here off camera and counted, and every number from 0 to 23 is showing up at least once here. And so I would interpret this as valid indices. So there we go. Again, there was a bit of grunt work today, but basically what we did is we loaded in a binary file, we investigated certain regions of that binary file, and got them into nice data that we could use. So hopefully you are feeling more confident working with binary files, and now that we have GLTF and binary under our belt, we should be able to load in a basic file with no animation and just get that on the screen. So that's what we'll be looking at in the next video. Anyway, all the best, have fun, and I'll see you again soon. Bye.